What if the stars you see, twinkling peacefully above you each night, aren't the gentle, constant companions we've always believed them to be? What if those pinpricks of light hiding in the velvet darkness are actually cosmic time bombs, stellar furnaces burning at temperatures that would vaporize our entire planet in microseconds? Or perhaps something even more mysterious, beacons from civilizations long dead, their light arriving as epitaphs written across the cosmos. Tonight, we venture into the serene yet terrifying realm where bedtime stories about wishing upon stars crumble, and the violent, magnificent reality of stellar physics takes root. We'll explore 100 facts about stars that will fundamentally change how you see the night sky. Some will comfort you. Others will keep you awake pondering humanity's place in an incomprehensibly vast universe. But all of them reveal that the sleepy stars above are anything but dormant. Consider this. Every star you've ever seen with your naked eye could already be dead. The light from even our closest stellar neighbors takes years to reach us. Betelgeuse, that reddish star in Orion's shoulder, could have exploded into a supernova yesterday, and we wouldn't know for another 650 years. You might be looking at a cosmic ghost, a stellar obituary that hasn't been delivered yet. The sky could be filled with phantoms, and we'd have no way of knowing until their final death screams reached our telescopes. But what if it's worse than that? What if stars aren't just dying in silence across the galaxy, but doing so in patterns we haven't yet recognized? What if the stellar deaths we observe are orchestrated, following rules we don't understand, perhaps rules that govern when and where life itself can exist? The implications would shatter our understanding of cosmic safety, of our place in the universal timeline, of everything we thought we knew about the long, slow evolution of the cosmos. We call them fixed stars, those eternal lights that ancient civilizations used to navigate oceans and mark the passage of seasons. But the universe knows no such thing as fixed or eternal. Stars are born in violent cosmic storms, live lives of unimaginable fury, and die in explosions that outshine entire galaxies. The peaceful night sky is an illusion, a trick of distance and time that masks the chaotic dance of stellar evolution happening all around us. Some stars spin so rapidly they flatten into disks, rotating hundreds of times per second, warping space-time itself into spirals. Others are locked in deadly embraces, cannibalizing their companion stars in slow-motion acts of cosmic vampirism. There are stars that shouldn't exist according to our understanding of physics. Stars too old, too massive, too strange to fit into our carefully constructed models of stellar evolution. Each anomaly raises uncomfortable questions about how much we really understand about these fundamental building blocks of the universe. And here's where it gets personal. You are made of stars. Every atom in your body, except hydrogen, was forged in the nuclear furnaces of stars that died before our sun was born. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was created in stellar cores under pressures and temperatures we can barely simulate in our most advanced laboratories. You are, quite literally, animated stardust, cosmic debris given the gift of consciousness. When you look up at the night sky, you're looking at your ancestors, your origin story written in light across billions of years. But this connection comes with a darker implication. If we're made of stars, then we're also subject to the same cosmic forces that govern their births and deaths. Our sun, that friendly yellow star that makes life possible, is middle-aged and growing warmer. In 1 billion years, it will have heated Earth beyond habitability. In 5 billion years, it will swell into a red giant, consuming Mercury, Venus, and possibly Earth itself. The star that gave us life will eventually take it all back. Our existence, our civilizations, our entire species, all of it is a brief flicker between stellar events, a temporary arrangement of atoms waiting for the universe to reclaim them. This isn't science fiction. This is observable, measurable reality, happening right now above your head. While you sleep, stars are being born and dying. Neutron stars are colliding, and creating the heaviest elements in the universe. Black holes are devouring entire stellar systems, and the cosmic ballet continues with or without our observation, our understanding, or our consent. So, are you ready to learn 100 facts about stars that will make you see the night sky differently? Some will help you sleep, marveling at the beauty and elegance of cosmic physics. Others might keep you awake, contemplating the vast forces at work in a universe that doesn't care whether we understand it or not. Either way, you'll never look at a sleepy star the same way again. Before we dive deeper into this fascinating journey through stellar physics and cosmic mysteries, if you're intrigued by astronomy, astrophysics, and the profound questions about our place in the universe, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is where you're watching from and where you're located. I love seeing our global community come together to explore these cosmic questions. Perhaps you're watching this as a bedtime story, letting the stellar facts wash over you as you drift off. Or maybe you're wide awake, coffee in hand, ready to have your mind expanded by the realities of stellar physics. Tell me, what's your favorite star? Is it our sun, the star that makes everything possible? Is it Polaris, the faithful North Star that's guided travelers for millennia? Or perhaps it's one of the exotic stellar objects we'll discuss tonight, a pulsar, a magnetar, or a hypergent star that makes our sun look like a grain of sand on a cosmic beach. And if you appreciate the research that goes into these deep dives, synthesizing information from peer-reviewed journals, NASA databases, and the latest astronomical surveys, a like really helps the channel grow and lets me know you want more content exploring the mysteries of the universe. Now, let's continue our journey into the stellar realm. We have 100 facts to explore, and each one reveals another layer of the magnificent, terrifying, beautiful reality of stars. When you close your eyes and think of stars, what comes to mind? Most of us picture peaceful pinpricks of light, constant and comforting, twinkling gently above us as we drift off to sleep. The phrase sleepy stars evokes bedtime stories, nursery rhymes, and the gentle comfort of knowing that tomorrow night those same stars will be there, exactly where we left them. This is the popular conception, the cultural understanding of stars that's been passed down through countless generations. But is this peaceful image accurate? Let's examine what astronomers and astrophysicists actually observe when they study stars, and the answer might surprise you. According to NASA and every major astronomical institution on Earth, stars are anything but peaceful. They are colossal nuclear reactors, each one converting millions of tons of mass into energy every single second through nuclear fusion. The temperatures in their cores reach 15 million degrees Celsius, hot enough that matter can only exist in a plasma state, with electrons stripped from atoms, creating a seething soup of subatomic particles. Our sun, that star we rely on for warmth and light, is actually a medium-sized yellow dwarf star. Right now, at this very moment, it's converting 600 million tons of hydrogen into 596 million tons of helium every second. Those missing 4 million tons? They're converted directly into energy, according to Einstein's famous equation, E equals mc. That energy radiates outward, taking thousands of years to work its way from the core to the surface, then just 8 minutes to cross the 93 million miles to Earth. The scientific consensus is absolutely clear. Stars are not threats to us in the traditional sense. Our sun won't explode. It won't go supernova. It doesn't have enough mass for that spectacular fate. The reassuring official position from astrophysicists is that the sun will continue its stable fusion reactions for another 5 billion years, give or take a few hundred million. We have nothing to worry about in our lifetimes, our children's lifetimes, or the lifetimes of thousands of future generations. The sun's energy output is remarkably stable, varying by less than 0.1% over an 11-year solar cycle. Other stars pose even less immediate threat. The nearest star system to us, Alpha Centauri, is 4.37 light-years away. That's about 25 trillion miles. Even if something catastrophic happened there, we wouldn't know about it for over 4 years, and the physical effects would take far longer to reach us if they ever did. Space is vast, and that vastness is our protection. The cosmic distances between stars are so immense that stellar events rarely have immediate effects on neighboring systems. Major astronomical organizations constantly monitor stellar activity. The European Space Agency's Gaia mission has mapped over 1 billion stars with unprecedented precision. NASA's various orbital telescopes observe stars across the entire electromagnetic spectrum, from radio waves to gamma rays. If a nearby star showed signs of imminent explosion or unusual behavior that could affect Earth, we would know. The scientific community would raise alarms. There are protocols, contingency plans, and international cooperation agreements for astronomical threats. So you can rest easy, right? Stars are just doing their stellar thing, quietly fusing hydrogen into helium, shining steadily through the night, providing navigation points and romantic settings for proposals and first kisses. They're the backdrop to human history, the same stars that ancient Egyptians saw, that guided Polynesian navigators across the Pacific, that inspired Galileo to point his telescope skyward and begin the scientific revolution. But what if we're looking at this question the wrong way? What if the real concern isn't about physical danger, but about something more subtle, more profound, more unsettling? What if the threat of stars lies not in their potential to harm us, but in what they reveal about our cosmic predicament? Despite these reassuring facts about stellar stability and cosmic distances, what shadows might lurk in the implications of stellar physics? Every star in the night sky is a ticking clock, a reminder that nothing in the universe lasts forever. Each one is in a different stage of its life cycle, from newborn protostars still gathering mass from their natal clouds, to middle-aged stars like our Sun, to red giants in their death throes, and finally to the stellar remnants, white dwarfs, neutron stars, and black holes that represent the final stages of stellar evolution. The peace we perceive in stars might be the ultimate cosmic illusion. We're viewing stellar processes on human timescales, where a star's evolution seems glacially slow. But zoom out to cosmic time, and stars are flickering into and out of existence, like candle flames in a draft. In the time it takes you to watch this video, dozens of stars will have been born in the Milky Way, and dozens more will have died. The stellar nurseries in the Orion Nebula are birthing new stars, even as ancient red giants elsewhere in the galaxy are shedding their outer layers, creating beautiful but ephemeral planetary nebulae that will dissipate in mere thousands of years. There's a Japanese aesthetic concept called mono no aware, the bittersweet awareness of impermanence, the recognition that beauty is intensified by its transience. Perhaps that's the real nature of stars. They're not peaceful or threatening. They're simply temporary. Every star you see, including our Sun, is in the process of dying from the moment it's born. The nuclear fusion that makes them shine also consumes them, burning through their fuel at rates that seem impossibly slow to us, but are actually remarkably fast on cosmic timescales. So are stars peaceful? Yes, in the sense that they pose no immediate danger. But no, in the sense that they're actually massive nuclear explosions held together by gravity, slowly burning themselves out in the cold darkness of space. The truth, as always, lies in the perspective we choose to take. And that perspective is about to get much, much stranger as we explore what these stellar facts reveal about reality itself. Let's talk about numbers, because numbers don't lie, and the numbers associated with stars are almost incomprehensibly large. When we try to grasp stellar scales, our everyday experience completely fails us. We need new frameworks, new analogies, new ways of thinking just to wrap our minds around the basic physical properties of stars. Start with speed. Earth orbits the Sun at approximately 67,000 miles per hour. That's fast, about 90 times faster than a rifle bullet. You're racing through space right now at this incredible velocity. and you don't feel a thing because everything around you is moving at the same speed. But some stars make Earth's orbital velocity look positively sluggish. Pulsar PSRJ 1748-2446 AD, a neutron star discovered in a globular cluster, rotates 716 times per second. The surface of this star is moving at approximately 24% the speed of light. That's roughly 161 million miles per hour at the equator. If you could somehow stand on the surface of this pulsar, which you absolutely cannot, because the gravity would instantly crush you into a thin layer of neutrons, you would circle the entire star in less than 2 milliseconds. Now let's talk about size. Our sun has a diameter of about 864,000 miles. That's big. You could line up 109 Earths across the sun's diameter. The sun's volume could hold about 1.3 million Earths. It contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, moons, asteroids, comets, dust, and gas adds up to a mere 0.14% by comparison. But the sun is tiny compared to Hypergent stars. UY Scuti, one of the largest known stars, has a radius approximately 1,700 times larger than our sun. If you replace the sun with UY Scuti, its surface would extend beyond the orbit of Jupiter. The star's volume is so vast that it could contain approximately 5 billion suns. Think about that number. 5 billion. The mind recoils from numbers that large, but this is observed reality, not speculation. For a more tangible comparison, imagine the sun is the size of a regulation NBA basketball, about 9.4 inches in diameter. On that scale, Earth would be smaller than a peppercorn, about 0.08 inches across. The distance from Earth to the sun would be about 82 feet roughly, the length of a basketball court. But UY Scuti would be the size of a house, about 133 feet in diameter. The scale difference between Earth and stars isn't just large. It's categorically different, like comparing a bacterium to a whale. What about mass? The sun weighs approximately 210 kilograms. That's a 2 followed by 30 zeros. It's approximately 330,000 times more massive than Earth. But again, the sun is relatively small by stellar standards. R136A1, located in the Large Magellanic Cloud, has a mass of approximately 315 solar masses. This monster star is so massive that it's right at the theoretical upper limit for how large a star can be and still remain stable. The historical context makes these numbers even more remarkable. Ancient astronomers had no idea about stellar masses or sizes. They could only observe brightness and position. When Hipparchus created his star catalog in 129 BCE, he was working with naked eye observations, trying to categorize stars by their apparent brightness. It wasn't until the early 20th century that we developed the tools and understanding to measure stellar properties accurately. Harlow Shapley's work in the 1910s revealed the true scale of our galaxy, showing that it was far larger than previously thought, with the sun located far from the center. Edwin Hubble's observations in the 1920s proved that the fuzzy nebulae astronomers had been observing were actually entire galaxies, each containing billions of stars. The universe expanded dramatically in human understanding within just a few decades. But here's where the uncertainty comes in, and this is crucial. We're still refining these measurements. Stellar distances are difficult to measure accurately, beyond a few thousand light years. We use multiple techniques: parallax for nearby stars, spectroscopy for more distant ones, Cepheid variables as standard candles for galaxies, Type Ia supernova for even greater distances. Each method has error bars, uncertainties, assumptions that might not hold true in all cases. UY Scuti's size, for instance, has been debated. Different measurements have produced different results, with some suggesting it might be smaller than initially thought. Stevenson 2 to 18 might actually be larger, or perhaps Westerland 1 to 26. The point is, we're dealing with objects so distant and so large that even our best instruments struggle to measure them precisely. We're confident about the order of magnitude. These stars are definitely more than 1,000 times larger than the Sun. But the exact numbers? Those remain somewhat fuzzy. Temperature adds another layer of staggering numbers. The coolest stars, brown dwarfs, that barely qualify as stars, have surface temperatures around 500 degrees Celsius. The hottest stars, Wolf-Rayet stars nearing the end of their lives, can have surface temperatures exceeding 100,000 degrees Celsius. And that's just the surface. The core temperatures are far higher, reaching tens of millions of degrees in normal stars, and billions of degrees during supernova explosions. But what if these numbers hide something more? What if the extremes we observe, the fastest pulsars, the largest hypergens, the hottest Wolf-Rayet stars, are telling us something fundamental about the universe's limits? What if these aren't random variations, but clues to deeper physical laws we haven't yet understood? The numbers stagger us, yes, but perhaps they should also make us wonder, why these numbers and not others? Why is there a maximum stellar mass? Why do pulsars spin at 700 times per second, but not 7,000? The answers to these questions might reveal that the universe itself has structure and limits we're only beginning to glimpse. Now we venture into truly strange territory, because the universe has produced stars that challenge our understanding of stellar physics. These aren't speculative objects from the fringes of pseudoscience. These are actual observed stars that don't quite fit into our carefully constructed models of how stars should behave. They're the anomalies, the outliers, the cosmic puzzles that keep astrophysicists up at night. Let's start with SMSSJ 031300 36 to 670,839 3. Try saying that name 5 times fast. This star, discovered in 2014, is located in the constellation Hydrus, about 6,000 light-years from Earth. What makes it extraordinary? It's one of the oldest stars ever discovered, formed approximately 13.6 billion years ago, just 100 million years after the Big Bang. That's ancient, even on cosmic timescales, representing the first generation of stars born after the universe's creation. But here's the problem. According to our models of early stellar formation, this star shouldn't exist in its current form. First-generation stars should have been massive, metal-free behemoths that burned through their fuel quickly and exploded within a few million years. SMSSJ 031300 36 to 670,839 3 is a small, low-mass star that's been burning steadily for over 13 billion years. The chemical composition is wrong. The mass is wrong. Everything about it challenges what we thought we knew about the early universe. The star has essentially zero iron content, less than 1/10,000,000th the iron concentration found in our Sun. It's almost entirely hydrogen and helium, the primordial elements created in the Big Bang itself. This chemical signature tells us it formed from nearly pristine material. But how did such a low-mass star form in an era when stellar physics suggests only massive stars should have existed? Then there's Przybylski's star, officially designated HD 1065. This star, located about 370 light-years away in the constellation Centaurus, has one of the most bizarre spectra ever observed. Its atmosphere contains unusual quantities of rare elements including holmium, lutetium, and europium elements that have no business being in a star's atmosphere in such concentrations. Even stranger, some spectral lines suggest the presence of short-lived radioactive elements like actinium and protactinium. The problem? These radioactive elements have half-lives measured in years to decades. They should decay quickly and disappear. Their presence in a star's atmosphere implies either continuous production through some unknown process, or that our understanding of nuclear physics under stellar conditions is incomplete. Astrophysicist Antoni Przybylski discovered this star in 1961, and we still don't have a satisfactory explanation for its chemical peculiarities. Some scientists have speculated, and I emphasize speculated, that Przybylski's star might be consuming unusual material, perhaps even technology-rich debris from an advanced civilization. This is extremely unlikely, and not the scientific consensus. But the fact that such speculation exists at all tells you how puzzling this star truly is. The more mundane explanation involves unusual nuclear processes in the star's atmosphere or magnetic field effects we don't fully understand. But even these explanations remain incomplete. Tabby's star, KIC 8,462,852, captured public imagination in 2015, when Kepler's Space Telescope data revealed irregular, dramatic dips in its brightness, sometimes more than 20% at a time. This is unprecedented. When planets transit in front of stars, they typically cause brightness dips of 1% or less. Whatever was blocking Tabby's star was massive and irregular. Initially, scientists proposed natural explanations: comet swarms, dust clouds, planetary debris. But each explanation had problems. The dimming events weren't periodic, like you'd expect from orbiting objects. The star also showed long-term dimming over the century before Kepler observed it, dropping about 16% in brightness, another anomaly with no clear explanation. The most exotic explanation? An alien megastructure, possibly a partially constructed Dyson sphere designed to capture the star's energy. This hypothesis, proposed by Penn State astronomer Jason Wright, generated enormous media attention. To be clear, this is the least likely explanation, and subsequent observations have made it even less likely. The current leading explanation involves an unusual ring system or cloud of material, but Tabby's star remains incompletely explained. It's a reminder that the universe still holds surprises we're not equipped to understand immediately. Scholz's star presents a different kind of anomaly. About 70,000 years ago, this dim red dwarf star passed through the outer Oort cloud of our solar system, coming within 0.8 light-years of the Sun, the closest known stellar flyby in the Sun's history. This is remarkably close on cosmic scales, though still about 50,000 times the Earth-Sun distance. The anomaly isn't the close passage itself, which was only discovered in 2015 through detailed stellar motion analysis. The anomaly is that it happened at all. Space is vast, and stellar close encounters should be extremely rare. Yet here we have evidence of a star passing close enough to potentially perturb comets in the Oort cloud, possibly sending some toward the inner solar system. Did Scholz's star trigger any meteor impacts on Earth? Did ancient humans, already modern in behavior and cognition, notice new comets in the sky? This is speculative territory, but it raises profound questions about how cosmic events might have influenced human history in ways we've never considered. Every 70,000 years or so, we might expect another stellar close encounter. What will the next one bring? Magnetars represent perhaps the most extreme stellar anomalies: neutron stars with magnetic fields trillions of times stronger than Earth's. Strongest magnetic fields in the universe, in fact. These fields are so intense that they warp the quantum vacuum, affecting the very fabric of space around the star. Get within 1,000 kilometers of a magnetar, and the magnetic field would disrupt your atomic structure, pulling the electrons from your atoms, destroying your molecular bonds, reducing you to a dissociated cloud of particles. But here's the anomaly. We don't fully understand how magnetars form, or why they have such extreme magnetic fields. The leading theory involves rapid rotation of a newly formed neutron star, generating a dynamo effect, but the details remain unclear. Some magnetars show sudden starquakes, where the star's crust shifts, releasing enormous bursts of X-rays and gamma rays. These bursts, called soft gamma repeaters, can affect Earth's ionosphere even from thousands of light-years away. This unprecedented chemical signature opens doors to speculation. What if these stellar anomalies aren't just quirks of stellar physics, but evidence of processes we haven't discovered yet? What if the universe operates according to rules we haven't even imagined? And these strange stars are trying to teach us something fundamental about reality? The question isn't whether stars can surprise us. They already have, repeatedly. The question is, what other surprises are waiting in the dark, hiding in plain sight among the billions of stars we haven't studied closely yet? Let's directly address the physical threat that stars pose to Earth and human civilization. This bears repeating. We need to be clear-eyed and scientific about actual dangers versus speculative fears. So let's do the calculations, cite the experts, and give you the honest assessment. Can our sun destroy Earth? Yes, eventually, but not through explosion. The sun will not go supernova. This is one of the most important facts in all of astronomy for human concerns. Supernova occur when stars have sufficient mass, at least 8 to 10 solar masses, to create iron in their cores. Iron fusion consumes energy rather than producing it, causing the core to collapse and rebound in a catastrophic explosion. Our sun, at approximately 1 solar mass, will never reach this threshold. Dr. Katie Mack, theoretical astrophysicist and author of The End of Everything, has explained this clearly. The sun will die a relatively gentle death, astronomically speaking, becoming a red giant, shedding its outer layers, and then settling down as a white dwarf. The timeline for this is about 5 billion years. More immediately, what about solar flares? These are real, observable threats. The 1859 Carrington event, the most powerful solar storm in recorded history, caused aurora visible as far south as the Caribbean and disrupted telegraph systems worldwide. If a similar event occurred today, the electromagnetic pulse could damage satellites, disrupt GPS systems, and potentially cause widespread power grid failures. NASA and NOAA constantly monitor solar activity through spacecraft, like the Solar Dynamics Observatory and the SOHO mission. According to the National Academy of Sciences, a severe solar storm striking Earth today could cause $1 to $2 trillion in damage to electrical infrastructure, with recovery taking months to years. But this isn't an extinction threat. It's a technological disruption threat, serious but manageable with proper preparation. The likelihood? Major solar storms occur approximately once per century. We're overdue, statistically speaking, since the Carrington event was 165 years ago. However, space agencies worldwide are developing better forecasting capabilities and hardening critical infrastructure against electromagnetic pulses. The threat is acknowledged, studied, and being actively mitigated. What about other stars? Could a nearby supernova threaten Earth? Astrophysicists have calculated this precisely. A supernova would need to occur within approximately 50 light years to cause significant damage to Earth's biosphere, primarily by depleting the ozone layer and exposing the surface to harmful radiation. The good news: there are no supernova candidates within this kill radius. Betelgeuse, everyone's favorite supernova candidate, is 650 light years away. When it explodes, and it will, perhaps tomorrow, perhaps in 100,000 years, it will be spectacular. For weeks or months, it will be visible during daytime, possibly as bright as the moon. Ancient civilizations would have thought the world was ending, but it won't harm Earth. The distance is too great. We'll have a light show, nothing more. Dr. Phil Plait, astronomer and author of Death from the Skies, has calculated, even if Betelgeuse went supernova right now, the radiation would take 650 years to reach us, and when it did, it would be about as dangerous as getting a dental X-ray. You get more radiation from a long airplane flight. Gamma-ray bursts represent a more serious theoretical threat. These are the most energetic events in the universe, typically caused by hypernova explosions or colliding neutron stars. If aimed directly at Earth from relatively close range, say, within 5,000 light years, gamma-ray burst could strip away our ozone layer, cause mass extinction, and potentially sterilize half the planet facing the burst. But there are multiple safeguards here. First, Gamma-ray bursts are narrowly focused, like cosmic laser beams. The odds of one being aimed precisely at Earth are minuscule. Second, they're extremely rare. We detect them occurring in distant galaxies at a rate of about once per day across the entire observable universe. But the chances of one occurring in our galaxy in any given year are estimated at roughly 1 in a million. Third, we've identified the nearby stars most likely to produce gamma-ray bursts, and none are in threatening positions or orientations. The astrophysics community has studied this extensively. Research published in the journal Astrobiology by Brian Thomas and colleagues suggests that gamma-ray bursts might have contributed to the Ordovician extinction event 450 million years ago. But even this is speculative. The evidence is circumstantial at best. So here's the honest assessment. Stars pose no immediate threat to human civilization. The sun will continue shining steadily for billions of years. Solar storms are manageable technological challenges, not existential threats. Nearby stars show no signs of imminent explosion. Gamma-ray bursts are statistically unlikely to affect us. We are, for now and for the foreseeable future, cosmically safe from stellar violence. International cooperation reinforces this conclusion. The International Astronomical Union coordinates observations worldwide. Space agencies share data about solar activity. The Minor Planet Center tracks potentially hazardous asteroids, a far more immediate threat than stars. The scientific infrastructure exists to warn us of cosmic dangers, and that infrastructure is constantly improving. And this is crucial, what if the real worst case has nothing to do with physical danger? What if the actual threat from stars is more subtle, more insidious, more profoundly unsettling than mere physical destruction? What if the problem isn't that stars might kill us, but what they reveal about the universe we inhabit? Because here's what stars actually tell us. We live in a universe where life exists only in narrow windows of cosmic time and space. We're dependent on a single star for our existence, with no backup plan. Our sun's stability is temporary. The heavy elements that make up our bodies and our planet were created in stellar explosions that destroyed entire solar systems. We are the products of cosmic violence, living temporarily in a pocket of calm, waiting for the universe to resume its normal state of chaos. That, perhaps, is the real worst case. Not that stars will kill us tomorrow, but that they've already shown us our ultimate fate. The question is, what do we do with that knowledge? Let's venture into speculative territory here. But let me be absolutely clear. What follows is not mainstream scientific consensus. These are ideas that exist at the fringes of astronomy, proposed by credible scientists but not widely accepted. I'm presenting them not as truth, but as thought experiments, as ways of questioning our assumptions about stellar physics. What if stars aren't simply the nuclear furnaces we think they are? This question, strange as it sounds, has been seriously considered by some scientists exploring alternative models of physics. The mainstream model of stars' nuclear fusion, powered by the proton-proton chain and CNO cycle, is extremely well established. We've observed neutrinos from the sun's core, confirming that fusion is occurring exactly where we expected. We've recreated fusion in laboratories, in hydrogen bombs, in experimental reactors like ITER. The evidence is overwhelming. But science progresses by questioning even well-established models, by asking, what if we're wrong? Dr. Halton Arp, a respected astronomer who later became controversial, questioned conventional cosmology by suggesting that redshift might not entirely be due to cosmic expansion. His ideas were rejected by mainstream astronomy, but he represents an important principle. Credible scientists can and should question foundational assumptions, even when those questions seem outlandish. In that spirit, some physicists have explored whether stars could be powered by alternative mechanisms. Electric universe theorists, for instance, propose that electromagnetic forces might play a larger role in stellar dynamics than currently acknowledged. To be clear, This theory is not accepted by mainstream physics and has significant problems explaining observed stellar behavior. But it represents an attempt to think differently about cosmic phenomena. What if stars are not isolated objects, but nodes in a vast electromagnetic network spanning the galaxy? This is speculation built on some legitimate physics. We know that magnetic fields thread through interstellar space. We know that cosmic rays high-energy particles travel between star systems. Could there be energy transfer mechanisms we haven't detected, subtle interactions between stars that affect their behavior? Dr. Hans Alfvén won the Nobel Prize in Physics in 1970 for his work on magnetohydrodynamics, the study of magnetic properties of electrically conducting fluids. His work showed that electromagnetic forces can indeed play significant roles in cosmic plasmas. Some of his later, more speculative ideas about cosmology were not accepted by the scientific community, but his core insight remains valid. We might be underestimating electromagnetic effects in space. Another speculative direction. What if stars are conscious? This sounds absurd, I know, but let me explain the serious version of this idea. Panpsychism is a philosophical position held by some respected thinkers suggesting that consciousness might be a fundamental property of matter, present to some degree in all physical systems. If consciousness exists on a spectrum, could sufficiently complex physical systems like stars, with their intricate magnetic fields, plasma dynamics, and nuclear reactions, possess some rudimentary form of awareness? Dr. Gregory Matloff, a physicist at New York City College of Technology, published a paper in 2018 exploring whether stars might have a form of volition. He examined whether certain stellar movements might be influenced by some kind of proto-consciousness. His work was speculative, acknowledged as such, and received skeptically by the scientific community. But it represents legitimate inquiry into unusual possibilities. The idea isn't as crazy as it first sounds when you consider complexity. A single star contains approximately 10 atoms. That's a 1 followed by 57 zeros. These atoms are in constant interaction, creating magnetic fields, plasma currents, turbulent flows. The complexity of interactions in a star might exceed the complexity of a human brain by many orders of magnitude. Could this complexity give rise to emergent properties we haven't considered? Almost certainly not in any way we'd recognize as consciousness. The counter-evidence is overwhelming. Stars behave exactly as physics predicts based on fundamental forces. We don't need to invoke consciousness to explain stellar behavior. Occam's razor, the principle that simpler explanations are generally better, strongly favors. CONVNTION, stellar physics. But here's why these speculative ideas matter. They force us to question assumptions. What if we're not seeing the complete picture? History is full of scientific revolutions where established models were overthrown by new evidence. Newtonian physics seemed complete until Einstein showed otherwise. Our understanding of the atom seemed solid until quantum mechanics revealed the strange truth. What if stars are communication beacons? This is the SETI hypothesis, the search for extraterrestrial intelligence. Some scientists have proposed that advanced civilizations might manipulate stars to send signals across interstellar distances. The variations in brightness, the spectral signatures, the magnetic field configurations. What if some of these aren't natural but engineered? Dr. Freeman Dyson proposed in 1960 that sufficiently advanced civilizations might build megastructures around stars to capture their energy. These Dyson spheres would change how stars appear from a distance, potentially making them detectable as anomalous infrared sources. We've looked for such signatures in astronomical data, and Tabby's star briefly raised this possibility. But again, natural explanations are far more likely. Every anomalous stellar observation so far has eventually yielded to conventional physics explanations, even if those explanations are complex or involve rare phenomena. The universe doesn't need aliens to be strange. Ordinary physics makes it plenty strange already. Dr. Jill Tarter, longtime SETI researcher, put it well. The universe is under no obligation to make sense to us, but it consistently behaves according to physical laws. When we find something we don't understand, the right approach is more observation, better models, deeper physics, not jumping to extraordinary explanations. So where does this leave us? These speculative ideas, electromagnetic networks, stellar consciousness, alien manipulation, are almost certainly wrong, but they serve a purpose. They remind us that our understanding of stars, comprehensive as it seems, is based on observations from a single planet, spanning less than a century of serious astronomical study, using instruments that detect only certain portions of the electromagnetic spectrum. We're like people who have only heard orchestras through telephone wires, trying to understand symphonies. We're getting a lot of information, and our interpretations are probably generally correct, but we might be missing subtleties, overtones, harmonics that would reveal deeper patterns. The responsible approach is to remain skeptical of unconventional ideas while staying open to genuine anomalies. When Jocelyn Bell first detected pulsars in 1967, the signals were so regular that she and her advisor Anthony Hewish initially called them LGM1 for Little Green Men. They remained open to the extraordinary explanation while pursuing the evidence rigorously. Eventually, they determined that pulsars were rotating neutron stars strange enough without needing aliens, but still a revolutionary discovery. That's the spirit we should bring to stellar anomalies, radical open-mindedness combined with rigorous skepticism. Yes, stars are probably just what we think they are. But let's keep looking, keep questioning, keep testing our assumptions. Because the universe has surprised us before, and it will surprise us again. The key is being ready to recognize genuine surprises while filtering out wishful thinking and pseudoscience. It's a difficult balance, but it's essential if we want to truly understand the stars above us. Now I want to take you on a journey into purely speculative territory. What follows is not based on evidence. It's a thought experiment, a what-if scenario that explores the darkest implications of stellar physics combined with concepts from the fringes of astronomy and futurism. Consider this science fiction grounded in real physics, a way of exploring possibilities, not probabilities. What if the stars we see aren't just passive objects, but part of a vast, ancient mechanism we don't understand? What if stellar evolution follows patterns that suggest something is deliberately managing stellar life cycles across the galaxy? Let me walk you through this scenario step by step, acknowledging at each stage that this is speculation, not science. Start with a troubling observation, the Fermi paradox. If the universe is billions of years old and contains billions of potentially habitable planets, where is everybody? Why haven't we detected any signs of alien civilizations? One proposed solution is the Great Filter Sum catastrophic barrier that prevents civilizations from reaching advanced, spacefaring status. What if the Great Filter isn't a single event, but a timed mechanism? What if stars themselves are the enforcement mechanism? Consider this. Every star has a finite lifetime. The heavy elements necessary for complex life are only created in stellar cores and supernova. This means technological civilizations can only arise after multiple stellar generations. You need the universe to age enough that metals exist. But stars also impose time limits. Main sequence stars like our Sun remain stable for billions of years, providing stable conditions for life to evolve. But once life becomes technological, it faces a ticking clock. The star will eventually die, and if the civilization hasn't achieved interstellar capability by then, it's trapped. Now add another layer. What if stellar deaths aren't random but coordinated? What if there's a pattern to supernova, gamma-ray bursts, and other stellar catastrophes that we haven't recognized because we're looking at too small a sample size? From our perspective, stellar deaths appear random, but we've only been doing astronomy for a few centuries. What if there's a cycle that operates on timescales of millions or billions of years? Let's make this more specific and more unsettling. Imagine a civilization far older than humanity, spread across the galaxy billions of years ago. They reached a level of technological advancement we can barely imagine. The ability to manipulate stars, to engineer stellar evolution, to use stars as tools rather than merely observing them. This civilization could have discovered something fundamental about the universe that we haven't. Perhaps that consciousness at galactic scales poses some kind of threat. Perhaps they learned that when too many technological civilizations exist simultaneously, they disrupt some essential balance in the cosmos, maybe through their collective use of energy, maybe through manipulation of quantum fields, maybe through something we don't have concepts for yet. So they implemented a solution. They engineered the stars themselves to serve as a regulatory system. Not all stars, that would be too obvious, but certain strategic stars at key locations throughout the galaxy. These stars would be altered at the quantum or subatomic level in ways we couldn't detect with current instruments. The alterations would be designed to trigger catastrophic events, supernova, gamma-ray bursts, extreme solar flares whenever nearby civilizations reached certain technological thresholds. How would this work? Consider that we're just beginning to understand quantum entanglement and non-locality. We know that particles can be correlated across vast distances in ways that seem to violate our intuitive understanding of space and time. What if sufficiently advanced technology could create entangled networks spanning light years? What if stars could be quantum entangled with their surrounding regions of space in ways that make them sensitive to certain types of energy signatures, specifically the energy signatures of technological civilizations? In this scenario, when a civilization advances to the point where its energy consumption reaches a threshold, perhaps when it begins to approach Kardashev Type I status, capable of utilizing all energy available on its home planet, this triggers a quantum response in nearby engineered stars. The star begins to destabilize. Solar flares increase. Stellar output becomes erratic. Eventually, if the civilization doesn't detect the warning signs and reduce its energy consumption or migrate, the star undergoes a catastrophic event. From the outside, this would look completely natural. We'd observe a supernova or gamma-ray burst, analyze the physics, and conclude it followed normal stellar evolution. We'd never suspect it was triggered by an external mechanism, because the trigger would be operating at a level of physics we haven't discovered yet. This would explain the Fermi paradox. Civilizations aren't rare. They're being systematically prevented from becoming spacefaring. Every time a species reaches a certain technological level, their star betrays them. The galaxy is filled with ruins, with planets bearing the remnants of civilizations that got just far enough to understand what was happening before being sterilized by their own sun. Now, let's apply this to Earth. Our sun is stable, showing no signs of unusual behavior. But what if that's because we haven't yet crossed the threshold? What if there's a specific technological capability, perhaps quantum computing at a large enough scale, perhaps artificial general intelligence, perhaps some form of energy generation we haven't invented yet that will trigger the sun's programmed response? And here's the truly dark implication. What if some civilizations have figured this out? What if they've detected the pattern, understood the mechanism, and made a choice? They could pursue technology aggressively, accepting that they're racing against time before their star destabilizes, hoping to achieve interstellar capability before the catastrophe. Or they could deliberately limit their technological development, living sustainably but primitively, avoiding the trigger, but also trapping themselves on their homeworld forever. This would create a cosmic tragedy. The very technological advancement necessary to escape the trap is what springs it. You need advanced technology to build interstellar spacecraft, but developing that technology starts a countdown to your star's destruction. It's an impossible dilemma designed by an ancient intelligence to ensure that the galaxy never becomes crowded with competing civilizations. The few civilizations that solve this puzzle, that manage to reach space before their star kills them, would be the ones that develop technology at exactly the right pace. Too slow, and their star dies of natural causes before they escape. Too fast, and they trigger the mechanism prematurely. There's a Goldilocks zone of technological development, and most civilizations fall on either side of it. Let me be absolutely clear. This scenario has zero evidence supporting it. None. It's pure speculation, drawing from real physics concepts, quantum entanglement, stellar engineering, the Fermi paradox, but weaving them into a narrative that is almost certainly fiction. The odds that stars are engineered enforcement mechanisms for a galactic regulation system are vanishingly small. But here's why I've walked you through this dark speculation. It illustrates how much we don't know. The scenario I've described is probably wrong, but something might be going on that we haven't imagined yet. The universe consistently surprises us. Black holes, dark energy, quantum mechanics reality is stranger than we expected at every turn. Stars might not be enforcement mechanisms. They're probably just natural nuclear reactors, exactly as physics tells us. But they're also markers of our place in cosmic time, reminders of our dependence on forces beyond our control. And perhaps, just perhaps, they hold secrets we haven't yet learned to recognize. The worst-case speculative scenario isn't that stars will kill us through some malicious mechanism. It's that we're living in a universe with rules and patterns operating at scales we can't perceive, and our technological development might have consequences we haven't considered. Not because of ancient alien engineering, but simply because we're part of a cosmic ecosystem whose dynamics we're only beginning to understand. That's the real nightmare scenario. Not hostile aliens or engineered stars, but our own ignorance about the systems we're embedded in. We're children playing with fire, not because the fire is malicious, but because we don't fully understand combustion. And the stars, those ancient lights above, might be trying to teach us something we're not yet wise enough to learn. Let's return to firmer ground and explore a concept that, while speculative, is taken seriously by scientists and philosophers: the Great Filter. This idea, first articulated by economist Robin Hanson in 1996, attempts to resolve the profound puzzle of why we haven't detected evidence of alien civilizations, despite the universe's vastness and age. The basic logic is simple and disturbing. The Milky Way galaxy contains an estimated 100 to 400 billion stars. Many, perhaps most, have planetary systems. Estimates suggest there could be 40 billion Earth-like planets in our galaxy alone. Even if only a tiny fraction of these develop life, and an even tinier fraction of those develop intelligent life, we should expect thousands or millions of technological civilizations in the galaxy. The universe is approximately 13.8 billion years old. Our sun formed about 4.6 billion years ago, making it a relative newcomer. Many stars in the galaxy are billions of years older. If civilizations developed around those older stars, they've had billions of years head start on us. A civilization even a few thousand years more advanced than us should be capable of interstellar travel. A civilization millions of years older should be unimaginably advanced, potentially colonizing entire galaxies. So where are they? This is the Fermi paradox, named after physicist Enrico Fermi, who allegedly asked this question during a lunch conversation in 1950. The silence is deafening. We've searched for radio signals, optical signals, infrared signatures of megastructures. We've analyzed thousands of star systems for signs of artificial construction. We've found nothing. The Great Filter hypothesis proposes that there must be some barrier, some critical step in the evolution from non-life to galaxy-spanning civilization that is extremely difficult or impossible to pass. Either we're extraordinarily lucky to have passed it already, or it's still ahead of us and likely to destroy us. Consider the steps required. 1. Right stellar system with stable star and appropriate planets. 2. Life emerging from non-life, abiogenesis. 3. Simple cells evolving into complex cells. 4. Multicellular life developing. 5. Intelligence emerging. 6. Technological civilization arising. 7. Civilization avoiding self-destruction. 8. Achieving interstellar capability. 9. Continuing expansion without catastrophe. Each step might be a potential filter. We know step 1 is common exoplanet surveys have confirmed that planetary systems are abundant. But we don't know about step 2. We have exactly one example of life emerging, Earth. We don't know if abiogenesis is common or extraordinarily rare. It might happen inevitably on any suitable planet, or Earth might be unique in the observable universe. If the filter is behind us, if one of the early steps is incredibly rare, then we can be optimistic. We've already passed the hard part. But if the filter is ahead of us, that's terrifying. It suggests that something catastrophic awaits technological civilizations, something so destructive that essentially none survive. What could this future filter be? Several candidates exist. Nuclear war. We've had the capability to destroy our civilization since 1945. We came frighteningly close during the Cuban Missile Crisis. As nuclear weapons spread to more nations, the odds of catastrophic use might increase. Climate catastrophe. We're conducting a global experiment by altering Earth's atmosphere. Maybe every technological civilization does this, and most fail to stop it in time, leading to runaway feedback loops that render their planet uninhabitable. Artificial intelligence. Perhaps the development of superintelligent AI is inevitable for technological civilizations, and perhaps such AI invariably decides that its creators are unnecessary or threatening. If advanced AI is developed before we understand how to make it safe, it could represent an extinction-level threat. Nanotechnology. Self-replicating molecular machines could, in a worst-case scenario, consume all organic matter on a planet, reducing it to gray goo. Any technology powerful enough to manipulate matter at the molecular level might also be powerful, enough to destroy civilizations that don't use it carefully. Biological weapons. As biotechnology advances, it becomes easier to engineer pathogens. A sufficiently advanced civilization might create a pathogen that escapes containment and sterilizes its homeworld. Resource depletion. Maybe civilizations inevitably consume their planet's resources faster than they can develop interstellar capability, leading to collapse. Or perhaps the filter is space itself. The distances between stars might be insurmountable. Even traveling at a significant fraction of light speed, journeys between stars take decades or centuries. Maintaining a technological civilization across such distances might be physically or economically impossible. Dr. Anders Sandberg, a senior research fellow at Oxford's Future of Humanity Institute, has studied this extensively. He notes, if the great filter is ahead of us, the implications are stark. Every time we develop a new powerful technology, nuclear energy, artificial intelligence, synthetic biology, we are rolling dice. We need to be right every single time. The filter only needs to catch us once. This raises profound questions about our astronomical observations. When we look at stars, are we looking at tombstones? Are those planetary systems out there hosting the ruins of civilizations that failed to pass through the filter? The galaxy might be filled with dead worlds, each one representing a species that got tantalizingly close to becoming spacefaring before being destroyed by their own technology, their own politics, or their own inevitable ecological collapse. There's a darker version of this idea called the Berserker hypothesis. Perhaps the great filter isn't passive, but active. Maybe the first civilization to achieve interstellar capability decided to ensure they never face competition. They created self-replicating probes, programmed to sterilize any planet showing signs of technological development. These Berserker probes might be out there right now, monitoring for radio signals, watching for chemical signatures of industrial civilization, waiting to strike. This sounds paranoid, but it's logically coherent. If you're a spacefaring civilization and you want to ensure long-term survival, eliminating potential competitors before they become threats is a rational strategy. Dark forest theory, articulated in Liu Cixin's science fiction novel, The Three-Body Problem, suggests that civilizations hide because making yourself known is inviting destruction. Could our stars give us clues about the great filter? If stellar phenomena are limiting factors, if gamma-ray bursts or supernova are more common than we think, sterilizing planets with developing life, then the filter might be environmental. Life might arise commonly, but rarely have enough stable time to reach technological capability before cosmic catastrophe strikes. Or maybe we're overthinking this. Maybe the great filter is simply that intelligent life is extraordinarily rare, and we're alone or nearly alone in the galaxy. This would be lonely but safe. If there's no one else out there, there's no filter ahead, no cosmic danger waiting. Just us, the stars, and billions of years to figure out our place in the universe. The stars can't answer this question. They just shine, indifferent to our fears and speculations. But studying them might help us understand which scenario is most likely, and that understanding could be crucial for our long-term survival. Every civilization that has ever existed has eventually ended. Egypt, Rome, the Maya, the Han Dynasty all rose to great heights and then collapsed or transformed beyond recognition. This is a historical pattern so consistent that it seems almost like a law of nature. Nothing lasts forever. But technological civilization is different, or at least we tell ourselves it is. We have science, global communication, nuclear weapons that enforce peace through mutually assured destruction, institutions designed to prevent collapse. We've identified existential risks and are working to mitigate them. Surely we're smarter than our ancestors, better equipped to avoid their fates? The stars suggest otherwise. They tell us that we're living in a narrow window of time, a brief moment of cosmic stability that won't last. Consider our sun's evolution. Currently, the sun is about 4.6 billion years old, roughly halfway through its main sequence lifetime. But that doesn't mean we have another 4.6 billion years of comfortable habitability. The sun's luminosity increases by about 10% every billion years as helium builds up in its core, changing the fusion dynamics. In approximately 1 to 2 billion years, the sun will be bright enough that Earth's oceans begin to evaporate. Water vapor is a greenhouse gas, creating a runaway feedback loop. The planet becomes increasingly hot and inhospitable. Eventually, all water is lost to space, broken apart by ultraviolet radiation. Earth becomes Venus a hellish, dried-out rock with temperatures high enough to melt lead. So our clock is already ticking. We have somewhere between 1 to 2 billion years before Earth becomes uninhabitable due to solar evolution. That sounds like plenty of time, but it's not infinite. And that's assuming we solve all our other problems first. Climate change, nuclear weapons, artificial intelligence, pandemics, asteroid impacts, resource depletion. Dr. Martin Rees, Britain's Astronomer Royal, argues in his book, Our Final Hour, that humanity has no better than a 50% chance of surviving the 21st century. That's a staggering claim from a serious scientist. He's not saying we're certainly doomed, but that the risks we face, technological, environmental, self-inflicted, are severe enough that our survival is genuinely uncertain. Think about the timescales here. Humans have existed in our current form for about 300,000 years. Civilization has existed for about 10,000 years. Industrial civilization is barely 200 years old. Nuclear weapons have existed for 80 years. We've had the capability to destroy ourselves for less than a single human lifetime. Where behavioral patterns evolved in the African savanna, trying to manage technologies that can alter the planet's climate or split the atom. We're tribal primates with access to weapons that can end all complex life on Earth. When you frame it that way, it's remarkable we've survived this long. The stars provide perspective on this. When we look at stellar evolution, we see inevitable patterns. Stars are born, mature, and die according to physics. They don't get a choice. They can't decide to burn more slowly or carefully manage their nuclear fuel. Their fate is determined by their mass and initial conditions. Are we similar? Is human civilization governed by similar inevitabilities? Do civilizations follow life cycle patterns as predictable as stellar evolution? Some scholars think so. Historian Arnold Toynbee studied the rise and fall of civilizations and identified patterns. Civilizations grow when they successfully respond to challenges, then decline when they fail to adapt to new challenges. Anthropologist Joseph Tainter argued that civilizations collapse due to diminishing returns on complexity as societies become more complex. They require more energy and resources to maintain themselves, eventually reaching a point where the cost of complexity exceeds its benefits. If these patterns are real, then technological civilization might face inevitable collapse regardless of our intentions. We might be in the late stages right now, without realizing it. The increasing complexity of our global system's financial markets, supply chains, information networks might be approaching the point where maintaining them costs more than they provide. And the stars watch indifferent. They've seen countless planetary systems form and die. If other civilizations have existed in our galaxy, they've watched those too, shining down on alien cities. Observing as those civilizations rose and fell, their radio signals eventually fading into silence. This is why some scientists argue for becoming a multi-planetary species as soon as possible. Not just because it would be cool to have cities on Mars, but because it's an insurance policy. If humanity only exists on Earth, we're vulnerable to any number of catastrophes. Asteroid impact, supervolcano eruption, runaway climate change, nuclear war, engineered pandemic. Spreading to multiple planets, multiple star systems even, would ensure that no single catastrophe could end human civilization entirely. But we're nowhere close to that capability yet. We haven't even managed a sustainable presence on the moon, and that's just 3 days away. Mars is at least 6 months' journey with current technology, and we don't know if humans can survive the radiation exposure during the trip or the reduced gravity long term. Interstellar travel remains firmly in the realm of science fiction. So we're stuck here on this one planet, circling this one star, with all our eggs in one cosmic basket. And the basket has an expiration date measured in hundreds of millions to billions of years. A long time by human standards, but a blink of an eye in cosmic terms. The philosophical question becomes, what do we do with this knowledge? Do we despair, concluding that everything we build will eventually be destroyed so nothing matters? Do we redouble our efforts, racing to develop the technologies needed to survive as a species? Do we accept our limitations and focus on making our temporary existence meaningful? Different thinkers offer different answers. Some argue for cosmic humility, accepting that we're temporary, that our impact will be finite, and that this is okay. Others argue for cosmic ambition, believing that intelligence and consciousness are precious in the universe, and we have a duty to preserve and spread them as far as possible. The stars don't care which philosophy we choose. They just continue their ancient cycles, burning fuel that was compressed in the universe's first moments, creating heavy elements that will form future planets and perhaps future civilizations. We're part of that cycle, temporary participants in a cosmic story that was unfolding for billions of years before we existed and will continue for billions more after we're gone. The question is, what will our chapter in that story say? Let's shift gears and ask a practical question. If there actually were strange patterns in stellar behavior, hidden messages in starlight, or anomalies that suggested something beyond conventional physics, how would we detect them? What are our institutional capabilities for recognizing cosmic anomalies? The answer is both reassuring and concerning. Our astronomical infrastructure is impressive, but it also has significant blind spots and limitations. Understanding these helps us assess how much confidence we should have in our current stellar knowledge. First, consider the detection methods. We study stars through several approaches. Photometry, measuring brightness over time. This is how we detect exoplanets through the transit method. When a planet crosses in front of its star, brightness dips slightly. Kepler and TESS satellites have monitored hundreds of thousands of stars this way. creating enormous datasets of stellar brightness variations. Spectroscopy, analyzing the light spectrum from stars to determine chemical composition, temperature, motion toward or away from us, and other properties. Every element produces unique spectral lines, creating a barcode we can read. This is how we know what stars are made of, despite never directly sampling their material. Astrometry, precisely measuring stellar positions and motions. The Gaia mission has done this for over 1 billion stars, creating a 3D map of the galaxy with unprecedented accuracy. This lets us track stellar motions, identify binary systems, and detect perturbations that might indicate unseen companions. Interferometry, combining light from multiple telescopes to achieve resolution equivalent to a much larger telescope. This allows us to directly image stellar surfaces, observing sunspots on other stars, and even creating rough maps of their surface features. But here's the catch. We're only looking at a tiny fraction of stars in detail. The Milky Way contains at least 100 billion stars. Even Gaia's billion-star catalog represents only 1% of the total. And most stars in Gaia's catalog are just position measurements. Detailed spectroscopic analysis exists for maybe millions of stars, 0.001% of the total. It's like trying to understand human civilization by closely studying 1,000 people out of 8 billion. You'd get general patterns, but you'd miss most of the diversity, most of the outliers, most of the interesting exceptions. If there are rare stellar phenomena occurring in 1 in 10 million stars, we've probably never observed one. If there's a pattern visible only when analyzing hundreds of thousands of stars collectively, we might not have the right data or analysis tools to detect it. If stellar anomalies occur on timescales longer than a human lifetime, our 100-year astronomical record wouldn't reveal them. There's also the problem of confirmation bias. We tend to see what we're looking for. When we observe stellar spectra, we're looking for known spectral lines of known elements. If there's something unexpected in the spectrum, some feature that doesn't correspond to any known atomic transition, it might get flagged as noise or instrumental error rather than a genuine anomaly. This has happened before. When Jocelyn Bell discovered pulsars in 1967, the signals were so regular that they briefly considered extraterrestrial intelligence as an explanation. They didn't jump to that conclusion. They carefully eliminated other possibilities first. But if the signals had been slightly less obvious, they might have been dismissed as interference or instrumental artifacts. Tabby's star is another example. It was flagged initially by citizen scientists in the Planet Hunters project who noticed the unusual brightness dips in Kepler data. Professional astronomers had looked at the same data, but hadn't flagged it as particularly interesting. Unusual doesn't always mean wrong, but it often gets treated that way until someone looks closer. Now consider institutional responses to genuine anomalies. Astronomy is generally an open, collaborative field. Data from major surveys, like Sloan Digital Sky Survey, Gaia, and Kepler, are publicly available. Citizen scientists can access the same data professionals use. This is good for transparency and reduces the chance that important discoveries are hidden or ignored. But there are also classification systems. Some astronomical observations are kept private temporarily, usually for 6 to 12 months, to let the discovery team publish their findings first. Military and intelligence agencies also monitor space, and their observations aren't publicly available. If a classified satellite detected an unusual stellar phenomenon, would we ever hear about it? Probably not immediately, but eventually. The astronomical community is global, and most stellar phenomena would be visible to multiple observers in different countries. Keeping something secret long-term would be difficult unless it was a one-time event, visible only from specific locations. The International Astronomical Union has protocols for announcing significant discoveries. If a nearby star showed signs of going supernova, for instance, there are established channels for rapid communication to the global astronomical community. These protocols exist and work well for known types of events. But what about truly unprecedented events? What if a star suddenly started emitting signals in a pattern that suggested intelligent origin? What if stellar spectra revealed evidence of elements that shouldn't exist? What if we detected a stellar phenomenon that violated known physics? This is where institutional response becomes harder to predict. Science is conservative, rightly so. Extraordinary claims require extraordinary evidence. But this conservatism can also mean that genuinely novel phenomena get dismissed initially because they don't fit existing frameworks. Consider the history of ball lightning. For centuries, people reported seeing glowing spheres of light during thunderstorms. Most scientists dismissed these reports as hallucinations or misidentifications because they couldn't explain ball lightning with known physics. It wasn't until the late 20th century that ball lightning was taken seriously, and even now, the phenomenon isn't completely understood. Could something similar happen with stellar anomalies? Could there be observations that don't fit our models, sitting in databases, waiting for someone to recognize their significance? Dr. Beatriz Villarreal leads a project called VASCO, Vanishing and Appearing Sources During a Century of Observations. That compares old photographic plates from the 1950s with modern surveys. They're looking for stars that have disappeared or appeared during the intervening decades. Most vanishing sources turn out to be artifacts in the old photographs or variable stars caught at different points in their cycles. But a few remain unexplained. What if one of these is genuinely anomalous? What if a star in the 1950s photographs really isn't there anymore? And not because it exploded or moved, but for some other reason we don't understand. The project is ongoing, and the researchers are cautious about claims. But it illustrates that we're still cataloging basic stellar phenomena. The problem is compounded by the sheer volume of data. Modern astronomical surveys generate petabytes of information. No human can examine all of it. We use automated algorithms to flag interesting objects, but the algorithms are only as good as their programming. If we don't know what we're looking for, we might not recognize it even when it's in front of us. Machine learning is helping. Astronomers are training neural networks to identify anomalies, objects, or patterns that don't fit known categories. This has led to discoveries of new types of variable stars, unusual galaxies, and other phenomena. But machine learning models also have biases based on their training data. They're good at finding things similar to what they were trained on, but might miss things genuinely novel. So, if stars harbor secrets, would we know? Maybe. Probably. If the secrets are obvious enough, if they're common enough that we've observed them multiple times, if they fit into frameworks we can recognize. But subtle secrets, rare phenomena, patterns visible only in aggregate data, those could easily slip past our current observational capabilities. This isn't a conspiracy. It's just the reality of doing science with limited resources on a cosmos vastly larger than our ability to observe it comprehensively. We're doing remarkably well with the tools we have, but humility is warranted. The universe has surprised us before, and it will surprise us again. The question is whether we'll recognize the surprises when they arrive, or whether they'll sit in datasets for decades, waiting for someone to ask the right question. We're past the halfway point in our journey through stellar facts, and it's worth stepping back to examine the emotional arc we've been walking. Fear and wonder, these are the twin responses that stars have always evoked in humans. Ancient peoples looked up and saw gods, omens, navigation aids. We look up and see nuclear furnaces, black holes, the birth and death of worlds. Which response is more appropriate? The case for fear is straightforward. Stars are violent on scales we can barely comprehend. A single solar flare can release energy equivalent to millions of nuclear weapons. Stars explode with such force that they briefly outshine entire galaxies. Gamma-ray bursts could sterilize Earth from thousands of light years away. Our sun, gentle as it seems, will eventually engulf our planet. On cosmic timescales, Stellar violence is the norm, and peaceful periods are brief exceptions. Moreover, stars remind us of our cosmic insignificance. We're temporary residents of a small planet, circling an ordinary star in an unremarkable region of a typical galaxy. The universe operated for billions of years without us, and will continue for trillions more after we're gone. Stars teach humility, sometimes harshly. But the case for wonder is equally compelling. Stars are the reason anything interesting exists in the universe. After the Big Bang, the cosmos was just hydrogen, helium, and traces of lithium. That's it. Everything else, the carbon in your DNA, the oxygen you breathe, the iron in your blood, the silicon in computers, was created in stellar cores or in supernova explosions. Every complex structure in the universe owes its existence to stars. Without stellar nucleosynthesis, there would be no planets, no chemistry complex enough for life, no consciousness pondering its origins. We literally wouldn't exist without stars, and not just because our sun provides light and warmth. We wouldn't exist because the atoms that make us wouldn't exist. Stars are also beautiful. The Orion Nebula, a stellar nursery where new stars are forming, glows in shades of red, blue, and green, visible to anyone with a small telescope. The pillars of creation in the Eagle Nebula showcase star formation, captured by the Hubble Space Telescope in images that became iconic of cosmic beauty. Supernova remnants like the Crab Nebula show the aftermath of stellar death in intricate, expanding shells of gas. This beauty isn't just aesthetic. It reflects underlying mathematical elegance, physical laws operating at extremes, the interplay of gravity, pressure, magnetism, and nuclear forces creating structures of extraordinary complexity. Stars are natural laboratories, where physics is tested at temperatures and pressures impossible to recreate on Earth. Dr. Neil deGrasse Tyson often speaks about this duality. In his book Astrophysics for People in a Hurry, he writes, "We are star stuff, contemplating star stuff. We are the universe made manifest, trying to understand itself. This captures the profound strangeness of consciousness arising from stellar remnants, of atoms arranged in such a way that they can question their own origins. Perhaps the balance is this: stars are indifferent to us. They don't hate us or love us. They follow physics, nothing more. Our fear and wonder are entirely human projections, emotional responses to physical phenomena that simply exist. But these emotional responses matter because they motivate us. Wonder drives scientific inquiry. Every astronomer who chose their career was moved by some moment of awe, some glimpse of cosmic beauty or mystery that made them want to understand more deeply. Fear drives caution, making us take seriously the risks we face and work to mitigate them. The key is not choosing between fear and wonder, but holding both simultaneously. Yes, the universe is dangerous and uncaring. And yes, it's also beautiful and comprehensible. Both truths can coexist. Consider the recent images from the James Webb Space Telescope. The deep field images show galaxies billions of light years away, containing billions of stars, each potentially hosting planetary systems. The sheer scale is dizzying, frightening even. But the images are also breathtakingly beautiful, revealing structures we've never seen before, answering questions we've asked for decades while raising new ones. This is the essential nature of scientific exploration of stars. Every answer generates new questions. Every discovery reveals how much more there is to learn. The frontier keeps expanding ahead of us, always remaining frontier no matter how far we push into it. Some people find this frustrating. They want definitive answers, complete understanding, an end to uncertainty. But the ongoing mystery is actually what makes stellar astronomy exciting. If we knew everything about stars, the field would be dead. The fact that we're still surprised, still discovering, still refining our understanding, that's evidence that the universe is deep enough to support unlimited inquiry. Practically speaking, this balance between fear and wonder should guide how we approach cosmic risks. We should take seriously the dangers that stars pose: solar flares, eventual solar death, gamma-ray bursts, while not becoming paralyzed by fear. We should develop technologies to detect and mitigate these risks where possible, while also celebrating the beauty and significance of stellar phenomena. The stars will continue to shine whether we fear them or admire them. Our response doesn't change their nature, but it does change us. Choose wonder, tempered with appropriate caution. Choose curiosity, tempered with humility. Choose to engage with the universe on its own terms, accepting that it's simultaneously more dangerous and more magnificent than we can fully grasp. That's the only reasonable response to stars. Acknowledge the terror, embrace the wonder, and keep looking up. Let's zoom out now and consider scale, not just the scale of individual stars, but the scale of the universe itself, and where stars fit into that incomprehensible vastness. Our Sun is one star among an estimated 100 to 400 billion in the Milky Way galaxy. Already, the numbers become difficult to grasp. If you counted one star per second, it would take over 3,000 years to count all the stars in just our galaxy. But let's continue. The Milky Way is one galaxy among an estimated 2 trillion galaxies in the observable universe. Some are smaller than ours, dwarf galaxies with only a few billion stars. Others are massive elliptical galaxies with trillions of stars. Taking a conservative average, the observable universe contains approximately 10 stars. That's a 1 followed by 24 zeros. A septillion stars. To put this in perspective, there are more stars in the universe than grains of sand on all the beaches on Earth. Every grain of sand on every beach represents multiple stars, each potentially hosting planetary systems, some perhaps with life, some perhaps with consciousness looking up at their night sky and asking the same questions we're asking. The distances involved are equally incomprehensible. Light travels at 186,282 miles per second, fast enough to circle Earth's equator 7 times in 1 second. At this speed, light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star, Proxima Centauri, takes 4.24 years. The Milky Way galaxy is about 100,000 light-years across, meaning light from one edge takes 100,000 years to reach the other edge. The Andromeda galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. When you see Andromeda in the night sky, visible even with naked eye from dark locations, you're seeing it as it was 2.5 million years ago. Humans didn't exist yet. Our evolutionary ancestors were just beginning to diverge from other great apes. The observable universe extends approximately 46.5 billion light-years in every direction, more than 13.8 billion light-years, which you might expect because space itself has been expanding during the time light has traveled. The most distant objects we can observe are so far away that their light has been traveling toward us for over 13 billion years. We're seeing them as they were when the universe was young, when the first stars and galaxies were just forming. This raises a profound point. The night sky is a time machine. Every star you see exists in the past. The light striking your eye right now left those stars years, decades, centuries, or millennia ago. You're seeing the past directly, laid out above you in a panorama of history. The present moment of distant stars is forever hidden from you because light has a finite speed. This means we don't even know the current state of the universe. We know what it was like in various past epochs, depending on distance, but the actual present state of the cosmos is unknowable. There's a sphere around us, expanding at the speed of light, beyond which we know nothing. We're living in a bubble of causality, connected only to regions of space within range of light-speed communication. Consider what this means for cosmic community. If a civilization exists on a planet 10,000 light-years away, any message they send will take 10,000 years to reach us. Our reply will take another 10,000 years to reach them. A single exchange of hello and hello back would span 20,000 years. No individual, no civilization as we understand it, could maintain a conversation across such timescales. This is the cosmic loneliness problem. Even if the universe is teeming with intelligent life, we might as well be alone because the distances are so vast that meaningful communication is impossible. We're islands in the cosmic sea, each able to see other islands but never reach them. Stars make this isolation more profound. They're our prisons and our lifelines simultaneously. We're bound to our sun, dependent on it for every calorie of energy that powers our biosphere. Breaking free of the sun's gravitational influence requires speeds we can barely achieve with our best rockets. Reaching another star would require either journeys lasting thousands of years or technologies we haven't invented, yet perhaps can't invent without violating physics. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object, about 14.5 billion miles from Earth. It's traveling at about 38,000 miles per hour. At this speed, if it were aimed at the nearest star, which it's not, it would take about 75,000 years to get there. In that time, entire civilizations would rise and fall. The English language would be long dead. Humans might have evolved into something unrecognizable. This is why science fiction's faster-than-light travel is necessary for space opera stories to work. Without it, the universe is simply too big for adventure. Real space travel is boring by narrative standards. Long periods of travel through empty darkness, arriving at destinations only to find more emptiness, perhaps with the occasional lump of rock or ice. But here's a thought that might shift your perspective. This scale is actually protective. The enormous distances between stars mean we're insulated from cosmic catastrophes. If a nearby star went supernova, we'd have years or centuries of warning as the light approached. If a hostile alien civilization existed, they'd face the same travel time problems we do. Distance is a shield, and the scale creates perspective on human concerns. Every war, every political conflict, every economic crisis, these happen on a planet that's invisible from even the nearest star. Carl Sagan famously called Earth a pale blue dot in a photograph taken by Voyager 1 from about 3.7 billion miles away. From that distance, Earth is less than a pixel, an insignificant mote in a sunbeam. Sagan wrote, "Look again at that dot. That's here. That's home. That's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. In the history of the species, the sum total of our joys and sufferings, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. This scale should humble us. It should make our petty conflicts seem absurd. But it should also inspire us, because we're part of this vast cosmos. We're the universe studying itself. And the stars, those ancient lights scattered across the cosmic dark, are our ancestors, our guides, and perhaps our destiny if we can find a way to reach them. After all this talk of cosmic violence, existential risks, and overwhelming scale, let's shift our tone. Because the story of stars isn't just about danger and mystery. It's also a story of incredible scientific achievement, of human cooperation, of mysteries solved and understanding gained. And that story offers genuine hope. Consider what we've learned about stars in just the last century. In 1920, we weren't even certain that other galaxies existed. The great debate between Harlow Shapley and Heber Curtis about the nature of spiral nebulae hadn't been resolved. We didn't know what powered stars' nuclear fusion wasn't understood until the 1920s and 30s. Cecilia Payne-Gaposchkin's 1925 thesis discovered that stars are primarily hydrogen and helium, contradicting the prevailing belief that stars had similar composition to Earth. Her findings were initially dismissed by senior astronomers, but were eventually confirmed and recognized as one of the most important astronomical discoveries of the 20th century. The cosmic distance ladder, our system, for measuring distances to stars and galaxies, was developed through painstaking work over decades. Harlow Shapley used Cepheid variables to map the Milky Way. Edwin Hubble used Cepheids to prove that Andromeda was a separate galaxy and discovered the universe's expansion. Each step built on previous work, creating a structure of knowledge that let us map the cosmos with increasing precision. The development of spectroscopy transformed our understanding. By the 1860s, astronomers could analyze starlight to determine chemical composition. Angelo Secchi created the first spectral classification system, grouping stars by their spectra. Annie Jump Cannon refined this into the system we still use: O, B, A, F, G, K, M, memorized by generations of students with "Oh, be a fine girl, guy, kiss me." Ejner Hertzsprung and Henry Norris. Russell independently developed the Hertzsprung-Russell diagram in the early 1900s, plotting stellar luminosity against temperature and discovering that stars fall into distinct groups: main sequence stars, giants, supergiants, and white dwarfs. This diagram revealed that stellar evolution follows predictable patterns, allowing us to understand a star's life cycle from a single observation. Each of these discoveries required international cooperation. Astronomers shared observations, data, and theories across borders and languages. World War I and World War II disrupted collaboration, but it resumed afterward, stronger than before. The International Astronomical Union, founded in 1919, coordinates astronomical research globally, ensuring that standards are maintained and discoveries are verified. This cooperation continues today at unprecedented scales. The Gaia mission is a European Space Agency project, but its data is used by astronomers worldwide. The Event Horizon Telescope, which captured the first image of a black hole in 2019, combined observations from radio telescopes across the globe, from Hawaii to Antarctica to Chile to Spain. No single nation could have done this alone. Citizen science has become increasingly important. Projects like Galaxy Zoo, Planet Hunters, and SETI at Home let ordinary people contribute to astronomical research. Henny's voorwerp, a unique astronomical object, was discovered by a Dutch schoolteacher participating in Galaxy Zoo. Tabby's star was flagged by citizen scientists analyzing Kepler data. This democratization of astronomy means more eyes on the data, more diverse perspectives, more chances to notice something unusual. It also builds public engagement with science, creating communities of people who understand the process of scientific discovery from direct participation. The transparency of modern astronomy is remarkable. Most major surveys make their data publicly available after a short proprietary period. Anyone can download Hubble images, Sloan Digital Sky Survey spectra, Kepler light curves. You can analyze the same data professional astronomers use, reach your own conclusions, even make discoveries. This openness stands in stark contrast to many other fields. Military technology is classified. Corporate research is proprietary. But astronomy, studying the most distant and universal phenomena, remains largely open. The cosmos belongs to everyone, and understanding it is a shared human endeavor. We've also made enormous technological progress. The James Webb Space Telescope, launched in 2021, is observing the universe in infrared with unprecedented sensitivity. It's seeing the first galaxies that formed after the Big Bang, analyzing exoplanet atmospheres for potential biosignatures, studying star formation in nearby nebulae with unprecedented detail. Ground-based telescopes continue to improve. Adaptive optics correct for atmospheric distortion, letting telescopes on Earth achieve resolution rivaling space telescopes. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter powerful enough to directly image Earth-sized exoplanets and study their atmospheres for signs of life. Multi-messenger astronomy is opening new windows. We don't just observe starlight anymore. We detect gravitational waves from merging neutron stars, neutrinos from stellar cores, cosmic rays from supernova. Each type of observation reveals different information, and combining them gives us a more complete picture of cosmic phenomena. The 2017 detection of gravitational waves and gamma rays from colliding neutron stars exemplifies this. Multiple observatories around the world, both ground and space-based, observed the event across the electromagnetic spectrum. We learned more from this single event than from decades of previous research on neutron star physics. And it confirmed that heavy elements like gold and platinum are created in these collisions, solving a long-standing mystery about the origin of these elements. This is science functioning at its best. International cooperation, open data, multiple lines of evidence converging on consistent answers, public engagement, technological innovation, driving new discoveries. And it's all happening right now in our lifetimes. We're living through a golden age of astronomy. What have we learned that gives us hope? Several things. First, the universe is comprehensible. Stars seemed mysterious and divine to ancient peoples, but we figured out how they work. We can predict their evolution, understand their composition, calculate their masses and distances. The cosmos operates according to physical laws that we can discover and understand through observation and mathematics. Second, humans can cooperate across borders to solve difficult problems. Astronomy doesn't care about nationality or politics. A photon from a distant star carries the same information whether detected in America, Europe, China, or Chile. This shared pursuit of knowledge creates connections that transcend political divisions. Third, we keep getting better at this. Our telescopes become more powerful, our detectors more sensitive, our analysis techniques more sophisticated. Problems that seemed intractable decades ago are solved. Mysteries that puzzled one generation are textbook knowledge for the next. Fourth, the universe is still full of surprises. We haven't figured everything out. There's always something new to discover, always another mystery to solve. This means there will always be room for curiosity, for exploration, for the joy of learning something no one has ever known before. Fifth, people care. When Hubble images are released, they go viral. When JWST observations show distant galaxies in unprecedented detail, millions of people look at the images, share them, discuss them. When we detect gravitational waves or find an interesting exoplanet, it makes news worldwide. Humanity is curious about the cosmos, engaged with the effort to understand it. This isn't naive optimism. It's recognition that alongside all the dangers and uncertainties, there's also genuine progress, real achievements, and reasons to believe we can continue learning, growing, and perhaps eventually reaching toward the stars ourselves. The challenges are enormous, but they're not insurmountable. And the effort to meet them brings out some of our best qualities: curiosity, cooperation, creativity, and courage. The stars witness our progress. They've watched us evolve from apes to astronomers, from firelight to starlight, from wondering about the heavens to actually studying them with instruments of exquisite precision. If stars could be impressed, perhaps they would be impressed by us. Let's get technical for a chapter and really understand how stars work, how we detect them, and how we've figured out so much about objects we can never directly touch. Stars are fusion reactors, but the process is more complex and fascinating than simple hydrogen fuses into helium. Let me walk you through what's actually happening in a stellar core. At the center of a star like our Sun, the temperature is approximately 15 million degrees Celsius, and the pressure is about 250 billion times Earth's atmospheric pressure at sea level. Under these conditions, Hydrogen exists as plasma electrons are stripped from protons, creating a soup of charged particles. For fusion to occur, protons must overcome electromagnetic repulsion. They're both positively charged, so they naturally repel each other. But at extreme temperatures, some protons move fast enough that when they collide, they can get close enough for the strong nuclear force to take over, binding them together despite electromagnetic repulsion. The Sun primarily uses the proton-proton chain. Two protons fuse to form deuterium, one proton, one neutron, releasing a positron and a neutrino. The deuterium fuses with another proton to form helium-3. Two helium-3 nuclei fuse to form helium-4, releasing two protons back into the mix. The net result: 4 protons become one helium-4 nucleus, with the mass difference converted to energy. But there's a catch. This process is incredibly slow. A single proton in the Sun's core waits, on average, billions of years before successfully fusing with another proton. The Sun only works because it contains so many protons, about 10 of them, that even with these terrible odds, the sheer volume of attempts means huge numbers of fusion reactions occur every second. More massive stars use the CNO cycle, carbon-nitrogen-oxygen cycle, where carbon acts as a catalyst. The process is more complex, but more efficient, allowing massive stars to burn through their fuel much faster than small stars like our Sun. The energy released in the core doesn't immediately reach the surface. It takes a tortuous path, bouncing through the star's interior. In the Sun, energy created in the core takes approximately 100,000 to 200,000 years to reach the surface. It travels through two zones: the radiative zone, where energy moves via electromagnetic radiation, photons bouncing off particles, and the convective zone, where energy is carried by hot plasma rising and cool plasma sinking, creating convection currents. When energy finally reaches the surface, it radiates into space as light. This is what we detect with our telescope's photons that began their journey in the stellar core hundreds of thousands of years ago, finally escaping to travel through space at light speed until some of them, by chance, strike our detectors. How do we know all this? We can't send probes into stars. They'd be vaporized instantly. Everything we know comes from remote observation and theoretical physics. Neutrino astronomy provides direct evidence of core fusion. Neutrinos are ghostly particles that barely interact with matter. Trillions of neutrinos from the Sun pass through your body every second without you noticing. Most pass through the entire Earth without interacting with a single atom. But by building enormous detectors filled with ultra-pure water or other materials in waiting, we can detect a tiny fraction of these neutrinos. The Homestake Mine experiment in the 1960s-70s first detected solar neutrinos, confirming fusion in the Sun's core. The detected number was lower than predicted, the solar neutrino problem, which eventually led to the discovery that neutrinos can change between different types. A breakthrough in particle physics that won the Nobel Prize. Helioseismology studies vibrations on the Sun's surface. The Sun rings like a bell, with different modes of vibration penetrating to different depths. By analyzing these vibrations, detected by measuring Doppler shifts in the Sun's surface, we can map the Sun's interior structure, test our models of solar physics, and even detect sunspots on the far side of the Sun before they rotate into view. Spectroscopy is our most powerful tool for understanding stellar composition. When atoms are excited, heated, electrons jump to higher energy levels. When they fall back down, they emit light at specific wavelengths characteristic of that element. Every element has a unique pattern of spectral lines, its fingerprint. By passing starlight through a spectroscope, essentially a sophisticated prism, we can spread it into a spectrum and read these fingerprints. We can identify not just which elements are present, but their relative abundances, the temperature and pressure where the light originated, whether the star is moving toward or away from us, Doppler shift, and even magnetic field strength through Zeeman splitting of spectral lines. This seems almost magical. From photons that have traveled across light years of space, we can determine the chemical composition of stars we'll never touch, measure their temperatures with precision, calculate their masses and distances, and track their motions through space. Binary stars are particularly useful. When two stars orbit each other, we can apply Kepler's laws to their orbits and calculate their masses directly. This is how we've calibrated our understanding of stellar mass-luminosity relationships. We can't weigh a single star directly, but we can weigh binary systems and work backward. Eclipsing binaries, where the stars pass in front of each other from our perspective, are even more useful. By measuring precisely how brightness changes during eclipse, we can determine stellar sizes, surface temperatures, and sometimes even map surface features. The tools continue to improve. Interferometry combines light from multiple telescopes, achieving resolution equivalent to a telescope as large as the separation between them. The Cara array on Mount Wilson can resolve surface features on nearby giant stars. We can literally see their surfaces, observing huge convection cells and measuring rotation rates. This is how we've learned so much about stars without ever visiting one. We use every messenger they send us photons across the electromagnetic spectrum, neutrinos, gravitational waves, and extract information with ever greater sophistication. We compare observations against theoretical models, refine both, and gradually build understanding that seems impossible from Earth's surface, but is actually robust and well tested. The physics of starlight isn't just academic knowledge. It's the foundation of our cosmic understanding, the basis for claiming we know what stars are made of and how they work. And it's verifiable. We can test our theories in laboratories, in particle accelerators, in the nuclear weapons tests that unfortunately confirmed our understanding of fusion. Stars are remote but comprehensible, and that comprehensibility is one of humanity's greatest achievements. Having looked at stellar physics and what we've learned, let's now look forward. What's next in stellar astronomy? What discoveries await us? What missions are planned that might reshape our understanding? Several major projects will come online in the next decade, each promising transformative capabilities. The Extremely Large Telescope, ELT, under construction in Chile's Atacama Desert, will have a primary mirror 39 meters in diameter, composed of 798 hexagonal segments. When it begins operations, currently planned for 2027, it will be the largest optical telescope ever built. Its light-gathering power and resolution will enable direct imaging of exoplanets, detailed spectroscopy of their atmospheres, and observations of the earliest galaxies formed after the Big Bang. For stellar astronomy specifically, the ELT will study star formation in unprecedented detail, resolve individual stars in nearby galaxies, allowing us to study stellar populations in different environments, and potentially detect the first stars formed after the Big Bang population 3 stars that should be massive, metal-free behemoths unlike anything in the modern universe. The Roman Space Telescope, formerly WFIRST, planned for launch in the mid-2020s, will conduct wide-field surveys in infrared, mapping billions of stars in the Milky Way. It will study stellar evolution, probe the galactic center region, currently obscured by dust-invisible light, and discover and characterize thousands of exoplanets through gravitational microlensing. The Laser Interferometer Space Antenna, LISA, planned for the 2030s, will detect gravitational waves from space. Unlike ground-based detectors like LIGO, which detect high-frequency gravitational waves from stellar mass objects, LISA will detect lower-frequency waves from supermassive black holes, extreme mass ratio in spirals, and potentially phase transitions in the early universe. For stellar astronomy, LISA will detect gravitational waves from white dwarf binary systems in our galaxy, providing a census of these stellar remnants. Ground-based gravitational wave detectors are being upgraded. LIGO's next-generation design, LIGO Cosmic Explorer, will increase sensitivity by a factor of 10, detecting neutron star mergers from across the observable universe. This will make such detections routine rather than rare, allowing statistical studies of how these events contribute to the cosmic abundance of heavy elements. Neutrino astronomy is expanding. The IceCube Neutrino Observatory at the South Pole detects high-energy neutrinos from cosmic sources. Planned upgrades will increase its sensitivity. Combined with gravitational wave and electromagnetic observations, neutrino detection enables true multi-messenger astronomy, where cosmic events are studied with every available messenger simultaneously. In stellar spectroscopy, extremely high-resolution spectrographs are being developed. These instruments can detect subtle spectral lines from trace elements, measure stellar surface velocities with meter-per-second precision, useful for detecting planets through Doppler wobbles, and analyze temporal variations in stellar spectra that reveal surface activity and internal dynamics. Artificial intelligence and machine learning are increasingly important. Modern surveys generate more data than any human could examine manually. Neural networks trained on known stellar types can classify millions of stars rapidly. But more excitingly, anomaly detection algorithms can flag objects that don't fit known categories, potentially revealing new types of variable stars, unusual chemical compositions, or phenomena we haven't theorized yet. The Vera C. Rubin Observatory, formerly LSST, beginning operations soon, will survey the entire visible sky every few nights, creating an unprecedented dataset of how the sky changes over time. For stars, this means detecting transient events, novae, supernova, stellar flares, characterizing all variable stars brighter than a certain limit, and potentially discovering rare phenomena that only reveal themselves through long-term monitoring. Exoplanet missions like Plato, planetary transits and oscillations of stars, will simultaneously study stars and their planets. By monitoring stellar oscillations, asteroseismology, Plato will determine precise stellar ages, masses, and radii crucial for characterizing the planets orbiting those stars. If we find a potentially habitable exoplanet, we need to know if its star is stable, old enough for life to have evolved, and not prone to sterilizing flares. The search for life beyond Earth increasingly focuses on stellar habitability. M dwarfs, red dwarf stars, are the most common type of star, and many have planets in their habitable zones. But M dwarfs are often active, producing frequent flares that could strip away planetary atmospheres. Understanding stellar activity across all stellar types is crucial for assessing which exoplanets might actually host life. Theory is advancing alongside observations. Computational astrophysics can now simulate stellar interiors, magnetic field evolution, and even entire supernova in 3 dimensions. These simulations, run on supercomputers, test our understanding of stellar physics under conditions we can't reproduce in laboratories. When simulations match observations, we gain confidence in our theories. When they don't, we know something's missing. One particularly exciting frontier, detecting population 3 stars. These hypothetical first-generation stars should have formed from pristine hydrogen and helium gas, with no metals whatsoever. They should be massive, tens to hundreds of solar masses, and short-lived, millions of years, ending in spectacular hypernovae that seeded the universe with the first heavy elements. We've never observed a population 3 star directly. They should have all died billions of years ago. But the most distant galaxies visible with JWST might contain these stars. Their spectra would be distinctive. No metal lines, extremely hot temperatures, unusual colors. Finding them would confirm our understanding of the earliest stellar generations and test cosmological models. Another frontier, stellar archaeology. The oldest stars still existing in the Milky Way metal-poor stars, like SMSJ 03130, 0.36670,839.3 discussed, earlier preserve information about the early universe's chemical composition. By studying these stellar fossils, we can learn what the universe was like when they formed, inferring properties of the even earlier stars that created the elements they contain. The European Gaia mission will continue releasing improved data. Its final catalog will include precise positions, motions, and distances for over 1 billion stars, creating a 3D map of our galaxy with unprecedented detail. This will reveal the Milky Way's structure, including stellar streams from devoured dwarf galaxies, spiral arm patterns, and the history of our galaxy's formation and evolution. Perhaps most exciting, we don't know what we'll discover. Every new instrument, every increase in sensitivity, every expansion of observed wavelength ranges has revealed surprises. Pulsars, gamma-ray bursts, fast radio bursts, magnetars, none of these were predicted before they were discovered. They emerged from observations and challenged us to understand them. What stellar phenomena await discovery? What types of stars exist that we haven't categorized yet? What processes occur in stellar cores that we haven't theorized? The universe has consistently surprised us, and there's no reason to think it will stop. The future of stellar astronomy is bright, perhaps literally so, as we discover ever more stars in ever greater detail, answering ancient questions while raising new ones that will drive research for generations to come. The stars have stories to tell, and we're finally developing the ability to hear them. We've journeyed far together through stellar realms, from the physics of fusion to the philosophy of cosmic loneliness, from gamma-ray bursts to gravitational waves, from ancient starlight to future discoveries. We've explored 100 facts about stars, some comforting, others unsettling, all revealing the magnificent complexity of the universe we inhabit. What have we learned? Stars are not the gentle, sleepy lights of bedtime stories. They're violent, energetic, constantly churning nuclear reactors that dominate their local environments through gravity and radiation. They're also beautiful, inspiring, and fundamentally responsible for our existence. Without stars, the universe would be a cold, dark expanse of hydrogen and helium, with no chemistry complex enough for life, no consciousness pondering cosmic questions. We've learned that stars follow predictable patterns. The life cycle from protostar to main sequence to giant to remnant is well understood from most stellar masses. But within this general pattern lies enormous diversity. Pulsars spinning hundreds of times per second, hypergens large enough to swallow Jupiter's orbit, magnetars with magnetic fields that warp space itself, bizarre chemical anomalies that challenge our understanding. We've learned that humans, despite being insignificant on cosmic scales, have managed something remarkable. We've figured out how stars work. From Earth's surface, using instruments that detect photons billions of years old, we've determined stellar compositions, masses, ages, and evolution. We've detected neutrinos from the sun's core and gravitational waves from merging neutron stars. We've imaged stellar surfaces and mapped entire galaxies star by star. This understanding comes with implications both humbling and empowering. We're humbled by the vast scales of space and time that dwarf human concerns. Every war, political crisis, and cultural upheaval happens on a planet invisible from even nearby stars. We're temporary residents of a cosmically ordinary star, living in a narrow window of that star's evolution when conditions happen to support complex life. But we're also empowered by our ability to understand. The universe is comprehensible, operating according to physical laws we can discover and test. Stars seem mysterious and divine until you understand fusion, spectroscopy, and stellar evolution. Then they become even more magnificent because you understand the mechanisms behind their beauty. We've explored some speculative and frightening scenarios: gamma-ray bursts, sterilizing planets, the Great Filter wiping out civilizations, possible patterns in stellar deaths we haven't recognized. These scenarios are mostly unlikely, but serve a purpose. They remind us that we don't know everything, that the universe might hold surprises, and that humility is appropriate when contemplating cosmic matters.